I have a coil in my hand. Agree? Can this thing store energy?
Yep.
Really? How?
Well, it has electrons in the metal.
Has electrons in the metal, so you could say it could store energy somehow by applying a voltage to one side. No, that's weird. So, yeah, making a comment that it does have electrons in the metal. Take some electrons out of this, and then you have a charged object. I guess that's energy stored, but it's not very good. I say that you can store energy. Can you store energy in a capacitor, Shiv?
What? Did you just say no?
Did you just say no?
No, I said yes.
Oh, okay.
No, you said no.
Oh my god.
You said no. Hold on.
Oh my god. All right. Okay, how do you store energy in a capacitor? Okay, so in what format is the energy stored? Like, why is it, like, conceptually, why is there energy stored in a capacitor? If you store energy in a capacitor, what form is that energy in? Uh-oh.
Oh, wow.
Do you know what a capacitor is?
So, I think you can read your lips.
Oh, man. All right, so let's say you had a plate of metal here and a plate of metal here. They're not touching each other. Could you charge it up? Could you charge up the plates?
Yeah.
So one's positive, one's negative. Why is there energy stored? The battery? The voltage difference. Okay, so you're saying there's an energy stored because there's a voltage difference between one plate and the other, if they're charged up. But if they're not charged up, there's no energy stored. Okay, good. I like that answer. That's a pretty good answer. All right? And if you wanted to step back even further, you could talk about the fact that these electrons are all bunched up and they want to spread out because they hate each other. Okay, good. So energy you can store in the capacitor. Good. Can you do the same thing with this device? Not exactly. Why not? Well, there's not two pieces of metal. This is all just one continuous piece of metal. So that doesn't work very well. But I say if you connect a circuit, you take some wire and do something like this, where you got, do I have a complete circuit now?
Yeah.
Yeah, I do. I got wire through the coil, comes out this post, connects to the other post, back through the coil again. This is a complete circuit. Would it be possible to store energy in this circuit?
It would all be.
Huh. Actually, yes, it is possible. Here's what you do. What you do is you somehow you hook up a battery or something inside this circuit. So, battery, where's the battery? I'm going to steal a battery out of the remote. I'm going to kill these batteries. Watch, I'm going to piss off the person who's in here after me. All right. Okay, check this out. I'm going to take a battery.
You want me to hold the battery?
Nah, it's okay. I don't want you to get burned if this goes wrong.
It's a okay, hold on. I don't think we're dealing with high enough voltages here.
To make a really hot battery?
Oh, not to make a really hot battery.
Oh, yeah. Yeah, this can make a really hot battery. Okay, I go like this. And I can make current flow in the circuit, right?
Yes.
Now, if I start current flowing in this circuit, doesn't that mean that this coil is going to become a magnet?
Yes.
Mm-hmm. Going to become a magnet, right? So if it becomes a magnet, let's say this is the north end of the magnet, the magnetic field comes out of the coil and flows back in around the other side of the coil. Agree? Okay. So doesn't that mean there's some flux through this hole?
Yes.
So there's some flux through the coil. It created its flux, but there is flux through the coil. Now, let's say that flux tried to get weaker. what would happen inside this coil? It's going to induce a current in this coil to try to mitigate the loss of energy, wouldn't it?
Yeah.
So it's going to mitigate, it's going to create a current. Which way is the induced current going to point? The same way that the current pointed that originally created the flux. So what does that mean?
Just keep
It maintains itself. It maintains its own current flow.
Forever.
Well, eventually it does lose energy, right? Because there's heat and stuff and energy loss. But this thing is a principle called self-inductance. It induces a current in itself that tends to maintain the current that was originally there.
So you can hook off the wires.
Now, if you unclip these wires, what's going to happen to the current?
It's not going to flow.
You can't have any current anymore because there's no loop. So yeah, the instant I unhook this thing, then it's done. The current's done. There's no more path for current to flow. But just as long as I kept a wire hooked up from one side to the other side, if I could get the field strong enough in here, the current would just keep on flowing and keep on flowing and keep on flowing and keep on flowing once I got it started.
So you want to do like an artificial magnet here?
This is a magnet, an artificial magnet.
Do you want to do like any other source of magnetic field?
No, this magnetic field was created from the current I put through
So
it.
could you create a permanent magnet by doing this, or no?
Well, how long is the current going to last?
Until it dissipates the energy.
Until all the heating in the wire just kind of resists and resists and resists the
okay.
current flow, and it's eventually going to get weaker and weaker and
So
weaker
if
and
you had
go
a
away.
superconductor, you could.
But this is going to store energy for a while. Yeah, if you did this with a superconductor, how long would the current last? Forever. Isn't that cool? So yeah, this is an energy storage device. If I kept it hooked up like this, I could carry it around the room, and by the time I got back to where I started, 10 seconds later, there would still be current flowing in this. Isn't that cool?
Mm-hmm.
All right, so that's called self-inductance. So what we're going to talk about today is this idea of inductance. You can induce a current flow, or an inductor, which is a coil that can maintain a current flow through itself. All right? And it's analogous to the idea of a capacitor, which maintains a charge difference, right? The capacitor maintains a charge difference. An inductor maintains current. All right, so an inductor, also known as a solenoid, which is just a coil of wire. What's the symbol for an inductor? A loopy, 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 right there. It looks kind of like you were to draw a resistor, except it's with little loops. All right, so what is an inductance? Well, if you had more coils, would you have more inductance? You think? More ability to induce whatever? Yeah, so an inductance is the amount of magnetic flux created by a certain amount of current. So more coils, that would mean more flux, yes.
Does it matter like the radius of the coils?
That's an interesting question. Does the inductance depend on the radius of the coils?
Yes.
I don't know. We'll figure that out. What do you think it does depend on?
The number.
The number of coils, probably.
Isn't there like just straight wire?
No, I think
Tiny little coils
wouldn't-
already.
No. Would the thickness
There's
of the
more
wire
area.
would matter?
Thickness of the wire
Would it?
for inductance? Remember, what's matters is how much of that magnetic field it's capturing, right, and holding on to. Maybe it has something to do with loop. Yeah, how tight they are, right? Remember when we did from before, when we did Ampere's law and we figured it out, it actually depends on N per L, loops per length. I have a hunch it might depend on that. All right. I also have a hunch that it might depend on what's in the middle of the coils. right? If you stuck a bunch of iron in here, would it work better?
Yes. It would.
Yeah, because it would concentrate the magnetic field, right? All right, so let's figure all that out. So inductance, it's the amount of flux you get for a given amount of current going through the coil. All right, so let's go back to that equation we had before. The magnetic field inside of an inductor is mu naught times the loops per length times the current, right? Now, also, we know, because of Faraday's law, or sorry, the definition of flux. The definition of flux is BA cosine theta, right? But assuming that it's all coming in just straight in the side, it's just B times A. And if you have N coils, it would be N times B times A, which is NBA, which has absolutely nothing to do with anything. All right? So that means that B would be equal to the flux divided by the number of coils times the area. So we get flux over NA equals mu naught NI over L. In other words, phi, or flux per current, must be equal mu naught N squared A over L. N squared A over L. Or what did we call flux per current again? What was that quantity? That's inductance. It's inductance. It's up here. So the inductance, if inductance is the flux divided by current, that means the inductance of this inductor is mu naught times the number of coils squared times the area divided by the length. Who said it depended on area? Was that you?
I asked you.
Yeah, and I said, I don't know. Guess what? It does. A bigger, wider, fatter inductor is a better inductor.
Because it captures more field.
Because it captures more. Yeah. Nice call. Well done. And what's the most important factor?
The number of loops.
Number of loops. If you have 10 times as many loops, what's that do?
100 times the
100 times the inductance.
But say you had a wire that was, say, half the diameter of
Yeah?
those wires, but you had the same amount of loops, would they have the same inductance?
Yeah, it would. It just would have more resistance, electrical resistance. All right, so here we go. Let's actually use this. So we're going to talk about capacitor versus inductor. And Shiv, this is the technical answer to the question I asked you. You ready? All right. A capacitor, where does it store its energy? Technically, if you ask a physics professor, what they're going to say is a capacitor stores the energy between the plates in the electric field. Isn't that interesting? So if a capacitor stores energy in its electric field, where does an inductor store its energy?
In the magnetic
In the magnetic field. Got it? Now, here's the other thing about a capacitor. I don't know if you know this. Sunjin, you know this. A capacitor, did you know you can't suddenly change the voltage across a capacitor? Really? Does it make... If you think about that, why would that be? Why can't you all of a sudden say, okay, now I want 100 volts less across this capacitor? Why can't you do that? Why is that physically impossible to do? Let me ask you this. What's on the plates of the capacitor? What's that? Okay, you have a positive plate and a negative plate. What's on those plates? And it starts with ch and rhymes with barges. Charges, right! All right, so you have charges on the plates. Why can't you suddenly change the voltage Say you have 100 volts difference on one side to the other side. Why can't you suddenly change from like 100 volts to like 0 volts on a capacitor? What would you actually have to do physically to that capacitor?
You have to take the charges.
You'd have to take the charges off. How long does it take to remove all those charges?
Probably forever.
No, it doesn't.
Well, by
Well,
hand.
no, charge distribution. I don't mean remove all its electrons. I mean just
Well, you have-
equalize the charges. In order to equalize the charges, if there's a lot of them, it's going to take a certain amount of time, right?
Yeah.
Therefore, it's going to take some time to drop the capacitor's charge to 0. And that's that whole time constant thing we talked about before, right? Guess what for an inductor? There's no charges stored, but there is current flowing. So, can you instantaneously change the amount of current flowing through an inductor? No, you cannot. Why not? It self-inducts, right. And so it's going to take some time to change the amount of current flowing through an inductor. Just like it takes some time to change the amount of charge on a capacitor, the voltage across a capacitor. All right? And so we've got this time constant thing we've got to deal with again. Yes?
If it's self-induct, how do you like force it?
Well, over time, it'll do the decay thing.
Can you like force it to go faster?
To go faster?
Or just, like,
Yeah.
okay.
Yeah, if you do something like jack up the resistance like crazy. And I'll show you a demonstration of that here in a bit. But for now, bear with me. So, you can't suddenly change the magnetic flux. You can't suddenly change the current in an inductor. So, that's kind of cool. That means an inductor tends to resist sudden changes in current. So if you want a circuit where the current is pretty steady and not wobbly at all, guess what you use? You put an inductor in. All right. So, let's take a look. There's equations that dictate this sudden change. The equations look like this. According to Faraday's law, the EMF induced across an inductor would be dphi over dt. Agreed? And according to the definition of inductance, if flux is the L times I, oh, by the way, inductance is L. Flux is L times I. That means the voltage across an inductor is dLi over dt. But we're going to assume this thing has a constant inductance. So the EMF across an inductor is equal to L di over dt. In other words, the voltage across an inductor is equal to the inductance of the inductor times how quickly current is changing. Wait a second. I need to show you a demonstration. I'm going to pause recording. Here's my inductor.
It's still going.
What's that?
It's still going.
Oh, still going. All right. So what we have here is we've got this coil. It's not hooked up to anything right now, except one of the wires is hooked up, but the other wire isn't. If I take the other wire and tap it, bam! I get arky sparky. Why? What's happening?
Black magic.
Now, how much current is going through this coil right now?
0.
0, right?
Correct.
Now, if I try to attach something to this, how much current is it trying to force to have happen? Say the resistance of this is, say this is 12 volts, and let's say the resistance of all of this is like, I don't know, what's a good number?
3.
So,
2 ohms. Let's go with 2 ohms for this class.
6 currents.
6 current.
6
Right, the
amps.
current would be 6 amps. So what did the current start at?
0.
0. What's the current going to end at?
6.
6 amps. And how quickly is it going to go from 0 to 6 amps?
Very quickly.
Very, very quickly. Let's see what this equation for voltage produced is. Okay, so here's the equation. The voltage produced is equal to blah, blah, blah times di over dt.
I thought the inductance.
What's di over dt?
The rate of change of the current.
How quickly the current's changing. So it's changing from 0 to 6 amps in how many seconds?
Like,
very,
2
very small
nanoseconds.
It's a really short time, right? Maybe a thousandth of a second.
Yeah.
So let's say it changed from 0 amps to 6 amps in 1/1000th of a second. What's the voltage?
6,000 volts.
That would be 6,000 times whatever the inductance is.
Can I touch this?
Wait, not yet.
Okay.
So, how many volts would we be produced? Let's say the inductance was 1.
6,000 volts.
That'd be 6,000 volts produced, which is that enough to make a spark?
Yes.
Yuppers it is. All right. So go ahead. Let's make some arky sparky. So my question is, does it work better with the metal core inside or not?
Yeah. It was vibrating.
Oh,
Oh, you can still touch the coils. How come you can still touch
Yeah, why are you
it?
touching it?
Isn't
Don't
there like
touch
a
it.
current going through it, Mr. Bruce?
let's see. It should get warm after a while.
Oh, it is. I feel it.
All right.
Oh.
So yeah.
How come you
Oh,
touch
wait,
it?
actually, this was a magnet, not just an iron core. Oh, well. I wonder if we have an actual,
that worse?
just non-magnetic
Iron ore.
Well, I don't want to demagnetize this by putting current through it the wrong way. Or putting magnetic field. But anyway, you guys got the point?
Yeah.
So this is a way to make a spark.
How quickly does the current go away?
Oh, well, if you remove it,
It's gone.
But
see?
doesn't it like self?
It should spark on the way out too, right? When I remove this,
Should.
watch. Did it?
Yeah.
Yes,
Doesn't it
did.
self-induct though? So
Because it
it will
wanted
take
to
a
connect,
while.
but then it was like, no, don't go.
Well, you're forcing the current to stop. That's the key, right? Because you're jacking up the resistance from like 2 ohms to like a bajillion ohms all of a sudden, because now it has to go from here to here through the air, and that's really difficult. So you're forcing the current to stop. And by forcing the current to change real fast, that means it's inducing a huge voltage difference and therefore creating a spark.
Oh.
So remember yesterday we talked about this theoretical problem where we had an airplane wing and flying it fast enough to get sparks to come off the tip?
Yeah.
Well, here's a way to make sparks that requires not going 50 million miles an hour. We actually, by the way, calculated it in 7th period, and it turns out you'd have to go like 50 million miles an hour in your airplane in Earth's magnetic field in order to get sparks off the tip of your wings.
How many?
not
Like,
that fast.
how much?
Like,
How much
Yeah.
voltage would you have to
I
induce in
drive
order to
faster
make
to
it
school.
fly
I
through
don't
the
know
air?
time.
Yeah, that's
Make
a
what
lot.
fly through the air?
The charge.
Oh, how much in order to get the arky sparkies? It depends on the geometry, but a couple thousand volts at least. Yeah. That's something we never actually did in electrostatics, but I love that question. It's like, let's say you had a sphere, and then if you just wanted static discharge into the air, could you calculate what the voltage difference would have to be on that between the sphere and infinity? And yeah, it's something like 20,000 volts.
Oh, okay.
Yeah. So yeah, we're getting, I don't know how many volts we're getting, but we're getting a lot. We're getting a lot more voltage difference between there and there than we are, I mean, this thing only supplies 12 volts. And that's very interesting. So it might be a 12 volt difference between here and here, but it might
How
be
come some of the sparks
a
are yellow and
50,000
some
volt
are blue?
difference there.
So if I touch it, I die.
Oh, that's a good question.
Don't try it. Why don't you try it?
Don't try it.
I used to know.
Because it is 50,000 volts.
Let's test it.
I don't know. If you had a 50,000 volt difference across you that was sustained, yeah, you would die.
So why
Anyone
don't
willing
I
to
die when I touch
volunteer?
it?
Oh, you
Pacemaker.
can touch that.
Why
Yeah,
wouldn't I
it
die
really
when I
across
touch
your
it?
heart. It would kill you.
So why wouldn't I die if I touch
So
it?
don't touch both
So,
sides.
so let's say this is at
So if I
this
touch
Zero.
is at 0 volts, and you stick your finger on it.
don't do it!
Why am I not dying right now?
It's not going through you.
What's my other hand
It's not
at?
going through.
Still at 0. So my left hand's at 0, my right hand's at
So it's all
0.
charged and
It's not going through
It's
you.
nothing.
If you were to
And
put
if I had my finger on here,
So what if I did like that?
There's
Don't-
no current.
don't do that. Don't do that. Yeah. Granted, it only happens for a very short period of time, like maybe a thousandth of a second. But I still wouldn't want to do that to you. All right, got it? Yeah. So, by the way, is there any practical applications for this?
Spark plug in a car.
Spark plug in a car.
Why
That's
do
how
you
you.
want a spark plug?
Because that's
To
what
start the
ignites
car.
your
Start the
engine.
car.
Well, no, not to start the car.
To ignite the
Ignite
gas
the-
in the
Every
engine.
time if you in a gasoline engine, every combustion that happens, every explosion, guess what starts that
A
explosion?
sparky plug.
That. A spark plug, and the spark plug works because of this principle. You've got a little inductor, a little coil, right?
Oh,
That
yeah.
wants to maintain itself at a nice, happy amount of current. And if you adjust the current in a thousandth of a second, then it's going to create a huge
Did you burn
voltage.
the
Yes.
alligator clutch?
All right. Let's go back to our seats. Okay, so we've got the basic idea that if you try to suddenly change the current through an inductor, it will fight back. It will fight back by creating a huge voltage difference, according to this equation, negative L over times di over dt. And it's the di over dt part that matters, right? If you have a very short time, you're going to have a huge voltage induced. All right, so spark plug. All right, so this is where we get into the problem-y stuff, and I'm going to let you read this mostly, but let's say you wanted to calculate the energy stored in the B field of the conductor, in the magnetic field of the inductor. We did something very similar for a capacitor way back when. All right, so here's how to do it. The power going into the inductor would be the current times the voltage difference, right? Which is the currents times the L di over dt. Now, power is the rate of change of energy, which means that the energy would be I times L times di. So if we integrate the amount of current from 0 to I, Li di, we get the amount of energy is 1/2 Li squared, which is shockingly similar to what Shiv said way back at the beginning about 1/2 CV squared. It's the exact same equation. It's just with L and I instead of C and V. All right, exact same equation. All right, so that's the one you're going to use a lot. And that's the end of the notes.